Scientists have discovered a vast, previously unknown reservoir of new aromatic material in a cold, dark molecular cloud by detecting individual polycyclic aromatic hydrocarbon molecules in the interstellar medium for the first time, and in doing so are beginning to answer a 3-decades-old SKI. We had always thought polycyclic aromatic hydrocarbons were primarily formed in the atmospheres of dying stars, said Brett McGuire, assistant professor of chemistry at the Massachusetts Institute of Technology, and the Project Principal Investigator for GOTHAM, or Green Bank Telescope, GBT, OBS. In this study, we found them in cold, dark clouds where stars haven't even started forming yet. Aromatic molecules, and PAHs, shorthand for polycyclic aromatic hydrocarbons, are well known to scientists. Aromatic molecules exist in the chemical makeup of human beings and other animals, and are found in food and medicines. As well, PAHs are pollutants formed from the burning of many fossil fuels and are even amongst the carcinogens formed when vegetables and meat are charred at high temperatures. Polycyclic aromatic hydrocarbons are thought to contain as much as 25% of the carbon in the universe, said McGuire, who is also a research associate at the Center for Astrophysics Harvard-Smithsonian, CFA. Now, for the first time, we have a direct window into their chemistry that will let us study in detail how this massive reservoir of carbon reacts and evolves through the process of forming stars and planets. Scientists have suspected the presence of PAHs in space since the 1980s, but the new res. To search out the elusive molecules, the team focused the 100 meters behemoth radio astronomy GBT on the Taurus Molecular Cloud, or TMC-1, a large, pre-stellar cloud of dust and gas located roughly 450 light-years from Earth that will someday collapse in on itself to form stars, and what they found. From decades of previous modeling, we believed that we had a fairly good understanding of the chemistry of molecular clouds, said Michael McCarthy, an astrochemist and acting deputy director of CFA, whose research group made the precise laboratory measurements that enabled many of these astronomes. What these new astronomical observations show is these molecules are not only present in molecular clouds, but at quantities which are orders of magnitude higher than standard models predict. McGuire added that previous studies revealed only that there were PA molecules out there, but not which. For the last 30 years or so, scientists have been observing the bulk signature of these molecules in our galaxy and other galaxies in the infrared, but we couldn't see which individual molecules made up that mass. With the addition of radio astronomy, instead of seeing this large mass that we can't distinguish, we're seeing individual molecules. Much to their surprise, the team didn't discover just one new molecule hiding out in TMC-1. Detailed in multiple papers, the team observed 1 cyanonaphthalene, 1 cyanocyclopentadiene, HC11N, 2 cyanonaphthalene, vinyl cyanoacetylene, 2 cyanocyclopentadiene, benzonitrile, trans, E, cyanovinyl acetylene, HC4NC, and propargyl cyanide, among others. It's like going into a boutique shop and just browsing the inventory on the front end without ever knowing there was a back room. We've been collecting little molecules for 50 years or so, and now we have discovered there's a back door. When we opened that door and looked in, we found this giant warehouse of molecules and chemistry that we did not expect, said McGuire. There it was, all the time, lurking just beyond where we had looked before. McGuire and other scientists at the GOTHAM project have been hunting for molecules in TMC-1 for more than 2 years, following McGuire's initial detection of benzonitrile in 2018. The results of the project's latest observations may have ramifications in astrophysics for years to come. We've stumbled onto a whole new set of molecules unlike anything we've previously been able to detect, and that is going to completely change our understanding of how these molecules interact with each other. It has downstream ramifications, said McGuire, adding that eventually these molecules grow large enough that they begin to aggregate into the seeds of interstellar dust. When these molecules get big enough that they're the seeds of interstellar dust, these have the possibility then to affect the composition of asteroids, comets, and planets, the surfaces on which ices form, and perhaps in turn even the locations where planets form within star systems. The Discover. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.